Hey, before anybody knows that you are struggling over confusion matrix, let's figure it out today. So in this video, I am gonna share my personal tricks so that this notorious stuff can never fool you out again. Sounds interesting, huh? Let's get started. So let's start with a binary classification problem. This is our dataset. We can see that the variable animal is the target variable and it can take only two values, either a cat or a dog. To run any supervised machine learning algorithm, we need to split our dataset into two parts, the training set and the testing set. Here we are using the 70-30 split rule. You can use a 60-40 or 80-20 rule or even any custom rule of your choice. Now we are gonna fit the model on the training set. This can be a logistic regression, support vector machine or any other model that falls under the umbrella of supervised machine learning. This fitted model would then be applied on the test set to check how well it performs in providing predictions about the animal class. In ideal conditions, the model would always provide accurate predictions. But in reality, it would occasionally provide inaccurate predictions as well. The frequencies of accurate and inaccurate predictions determine the performance of our chosen model. To evaluate model performance, we represent the actual class counts and predicted class counts in a two-dimensional matrix form like this. Here the convention is to represent the predicted class row-wise and actual class column-wise. It helps us to identify accurate and inaccurate classification counts pertaining to each of the classes. This matrix is termed as the confusion matrix. To understand the terminologies regarding confusion matrix, you need to determine which class is more important for your analysis. That class would be your positive class. In this example, the determination of positive class is kind of subjective. As a cat lover, I wish to take cat to be the more important class, hence positive. If you prefer dogs, you can change this accordingly. Conventionally, the chosen positive class should always be the first one to represent both row-wise and column-wise in a confusion matrix. In this matrix, the top left cell signifies those observations in the test set which the model could correctly classify as cats. These are called true positives. The top right cell represents those cases which the model incorrectly classifies as cats when they were actually dogs. For this, they are called false positives. I know these terms are intimidating. Please don't get stressed out as I would be sharing my special tricks in this single video, so keep watching. Similarly, the bottom left cell counts those cats that are incorrectly classified as dogs. These are called false negatives. The bottom right cell represents the frequency of correctly classified dogs. They are known as the true negatives. In this way, each cell of the confusion matrix is specific to a particular term. For a detailed discussion, let's proceed to the next section. Here comes the best part of this video that you won't find anywhere else. In this part, I would be sharing how to read a confusion matrix without memorizing anything at all. Suppose this is the confusion matrix that we are trying to read. Let's identify the true positives first. Here you can see the term true positives contain two parts. One is the true false part and the other is the positive negative part. The positive part indicates that the predicted class is positive, which is cat in our discussion. The true part indicates that this prediction is indeed true. Thus, to any cell in a confusion matrix, we need to ask two questions. Is the predicted class positive or negative? And is the prediction true or false? First, let's target this cell of a confusion matrix. Now, what is the predicted class of this cell? We can see that the predicted class is cat, which we have taken to be the positive class. Hence, the answer is positive. Now, let's move on to the next question. Is the prediction true or false? Here, notice that the predicted class level for the targeted cell matches with the actual class level. Hence, the prediction is true. In this way, we get the answers as positive and true. Compile them in reverse order, and now you get the term you are looking for, true positives. Thus, the top left cell of the confusion matrix has represented the true positives. Similarly, we target the top right cell. We try to answer the same two questions. Is the prediction positive or negative, and is the prediction true or false? The answer of the first question becomes positive as the predicted class level is cat. But here, the predicted class level does not match with the actual class level. Hence, the classification is false. Thus, compiling positive and false in reverse order, we reach at false positives. In this way, we get to know that the targeted cell represents false positives. Again, let's start with this cell. Answer the same questions. Here the answers are negative and false. Combining them, we get false negatives. Repeat the same procedure with the remaining cell of the confusion matrix. The answer of the two questions are negatives and true here. Compiling, where we understand what it represents. In this way, we reach at our thumb rule. Target any cell in your confusion matrix and answer these two questions with respect to that cell. Combine the answers in reverse order, and you get the term pertaining to that cell. Now you know how to avoid the most common errors while interpreting a confusion matrix. To tackle the remaining 1%, follow the next section. The rest 1% error emerges from wrong understanding of a confusion matrix when it is represented in heat map format. This is how you get to see most of the confusion matrices within a coding environment. But there is nothing to be confused here, as it is the same confusion matrix with only a color coding applied on top of it. This color coding is a function of the cell count. Generally, the higher observation count a cell has, the darker is the color applied. But it actually depends on the chosen color palette. There is no hard and fast rule here. By looking at this confusion matrix heat map, you can quickly say if your model is performing in a decent way or there is something wrong with it. If the top left and bottom right cells are much darker than the rest, there is nothing to worry about. Else, you need to check your model specifications. One humble request here is that please don't confuse confusion matrix with correlation matrix. Because yes, heatmap does represent correlation matrix sometimes, but sometimes it represents confusion matrix as well. And in case of confusion matrix, we are not dealing with correlation whatsoever. So that's all for today. If you want to learn more about confusion matrix, then I'd recommend you to watch my next video. The easiest way to get notified is, well, hit the bell icon after you subscribe.